Hello viewers, welcome to DSP lecture series. So in this video we are going to see about how to derive the signal to quantization noise for B and B+1 bits and state the assumptions made. Here B is nothing but the binary bits, that is excluding sign bit. B+1 is an binary size of binary including the sign bit. So for these two cases we are going to derive the quantization noise ratio. It's a very simple derivation. Here you know that the process of analog to digital conversion, that is in process of analog to digital conversion, that is involves sampling and quantizing the amplitude of the sample data. Okay, so in analog to digital conversion the two major processes are sampling and the quantization. That is, while quantization, that is quantizer rounds the sampled signal, the quantizer rounds the sampled signal to the nearest quantized level. So the general block diagram for this quantizer is a summer. So this is the input signal x of n. This one is the quantizer and this is a quantized output. Here, due to quantization process, definitely we may have some error. Okay, so the error is the quantized output, the difference between the quantized output and the input signal. While rounding, that is while rounding the levels, that is truncating or the rounding, during the rounding process, that is rounding is involved in the quantization process, that is rounding is involved in the quantization process. So the error, the range of error is in between minus 2 power minus b by 2 e of n less than or equal to 2 power minus b by 2. The next one is the error, the quantization error is assumed to be uniformly distributed. The quantization error is assumed to be uniformly distributed, that is uniformly distributed over this range. And then the power of next we are going to find the power of the quantization noise or quantization error, that is the power of the quantization noise. The power of the quantization noise, that is which is nothing but an variance, sigma e square. It is given by sigma e square is nothing but e of error signal square minus e square of e of n. Here the mean value of the error, that is when you see the distribution of this, when you see the distribution between error and then property of the error signal, when you see the distribution which is in between 2 power minus b by 2 to 2 power minus b by 2, the mean value is, what is the mean value of this region? The mean value is 0. The mean value is 0. Okay, so that the mean value of error e of n is equal to 0. So my error, that is the variance, is equal to e of e square of n, and my quantization step size, and then quantized step size, the quantized step size is expressed as Q is equal to a range divided by 2 power b. So b represent the binary bits which is excluding sine beta, that is a 2 power b. The range, you know that the range is in between minus 1 volt to plus 1 volt, so the range is equal to 2 volt. So Q is equal to 2 divided by 2 power b. And the quantization error for rounding will be the error for rounding. The quantization of the error, the rounding will be in the range minus q by 2 to plus q by 2. So from this, the variance of this error signal is equal to, there is a difference between these that is a total difference between these two, q by 2 minus of minus q by 2 integral minus q by 2 into plus q by 2, that is e square into dE. Then sigma e square, that is the variance, sigma e square is equal to, that is 1 by q, that is when you take the integral for q square, it is q cube by 3, sorry, e cube by 3 for the limit plus q by 2 minus q by 2. So apply the upper limit and the lower limit. I am taking 3q common outside. And then this one is a q cube by 8 minus of minus plus q cube by 8, which is equal to 2q by, that is a 24 into q, so which is equal to this one 12, this one q square, that is q square divided by 12. So this is the quantization noise. The quantization noise is equal to q square by 12. So substitute the value for q. We know that q is equal to the range we have already found, that is r divided by 2 power b. So that this one is equal to 2 power b square divided by 12. Then after some simplification, there is 4 divided by 2 power, that is a square of 2, that is a 2 power 2, 4. 2 power b is a 2 power 2b divided by 2, and after simplification it is 1 by 3 into 2 power 2b. So this is sigma e square. So we have to find the signal to quantization noise ratio. So SNR, signal to quantization noise ratio, is equal to signal variance divided by quantization noise variance, which is equal to sigma x square divided by 1 by 3 into 2 power b, and is equal to, which is equal to 3 into 2 power 2b into sigma x square. I am going to represent in terms of dB, SNR in dB, so which is equal to 10 into log of 3 base 10 plus 10 into log of 2 power 2b base 10 plus 10 into log of 2 power, sigma x square plus 10. Then for log 3 base 10 into log 3 and then multiply by 10, it is 4.77, and similarly 2 power b means 20b, log 2 into 20, it is equal to 6.02 b plus 10 into log sigma x square. So this is the signal to quantization noise ratio for b beta. Suppose in second case it is for b plus 1 bit. If it is for b plus 1 bit, the same thing. So you know that quantization noise is q square by 12, and then for b plus b plus 1 bit is equal to, for the same range, 2 power b plus 1 and then square divided by 12, which is equal to, that is 2 divided by 2 power b into 2 power 1. I am going to write this in 2 power b plus 1 as 2 power b into 2 power 1. So this will get cancelled, divided by 12, which is equal to 1 by 2 power, that is the square, 2 power 2b divided by 12. So it is equal to same thing. This is equal to the sigma e square is equal to sigma e square is equal to 1 by 2 power 2b into 12. Then the same process, that is signal to noise ratio, that is signal to quantization noise ratio for b plus 1 bit, that is SNR in dB, which is equal to signal variance divided by noise variance. So which is equal to sigma x square divided by, we have already found it as 1 by 2 power 2b into 12. So that it is equal to 12 into 2 power 2b into sigma x square. So in terms of dB, that is 10 into log 12 base 10 plus 10 into log 2 power 2b base 10 plus 10 into log sigma x square base 10. It is equal to, that is 6.0 dB, that is a 10 into log 2 power 2b base 10 is equal to dB plus 10.79, that is logarithmic value of 12 and multiplied by 10 is 10.79 plus 10 into log sigma x square by 10. So this is one of the university question. I summarize the answer for this question asked. Derive an expression for an signal to quantization noise ratio for b and b plus 1 beta. Here the quantization, that is for analog to digital conversion, there are two processes are involved. So one is the sampling and the other one is the quantizing. So while doing quantization process, that is either truncating or rounding, there may be some error. We are going to analyze what be the quantization error. So for the system, x of n be the input and xq of n be the quantized output, so that I am having the error as an e of n. So that the error is e of n is equal to xq of n minus e of n. The rounding, due to this rounding, the error is in the range of 2 power minus b by 2 to minus 2 power minus b by 2 to plus 2 power minus b by 2. I am assuming the error is uniformly distributed, and if it is uniformly distributed, then the mean of the noise is equal to 0. So from this, the noise variance is equal to e of e square of n minus e square of e for n. Here it is, the mean is equal to 0. So my quantization variance is sigma e square is equal to e into e square of n. So you know the quantized step size is equal to r by 2 power b. So r is the range. So here the range is, I am assuming the range is from minus 1 to plus 1. So r is equal to 2 volt. So q is equal to 2 power 2b. So this is the binary bits excluding the sign bit b. From that, the quantization error, the level is from minus q by 2 plus q by 2. So integrating for e square with respect to error. So after integrating it, a small integration, that is a e cube. So this one is the e cube by 3. Apply the limits so that my quantization error be q square by 12. Then I am applying the quantization level value as 2 power 2 by 2 power b. After some simplification, my error is 1 by 3 into 2 power 2b. Then I am finding the signal to quantization noise ratio. This is a signal variance and this one is the noise variance or error variance. And I am taking the logarithmic value to represent it as. For b bit, my signal to noise ratio is 4.77 plus 6.02b plus 10 into log sigma x square. For b plus 1 bit, so for b bit, For b plus 1 bit, 2 power b plus 1 square, same process. So my quantization error is 1 by 2 power 2b into 12. And then signal to noise ratio in terms of dB, I am taking the value in logarithmic scale. So my signal to noise ratio is 6.0 dB plus 10.79 plus 10 into log sigma x square. Here, so from this, the signal to noise ratio is increased approximately by 6 dB. So this is the conclusion of this question. The signal to noise ratio is increased approximately 6 dB for each bit added to register length. So this question is an university question. If you want more question, subscribe our channel. Thanks for listening. Thank you so much.